Okay, so today I want to talk about section 4.4, undetermined coefficients. So last week we started talking about linear constant coefficient, homogeneous or homogeneous differential equations. Okay, so that's basically this type of equation, but there's a zero here on the right-hand side. Okay, that's what makes it homogeneous. Okay, and we know how to find the solutions to that by forming the auxiliary equation and then finding the roots, and then depending on if the roots are distinct, real and distinct, real and repeated, or complex, then we get different types of solutions for the homogeneous equation. Now we want to try and solve this where it's non-homogeneous, where we have something else on the right-hand side, non-zero. Okay. In general, what this means is that the solution is going to have two parts. It's going to have the homogeneous solution, and then it's going to have a particular solution. Okay, so this y sub h solves the homogeneous equation. No, ay double prime plus by prime plus cy equals 0. Okay, so since this is linear, if we think about plugging in this whole solution here into this equation, the homogeneous part, if we plug it into the left-hand side, is just going to go to 0 because it solves this equation right here. So it doesn't really affect when we plug it into the left-hand side, we get a 0 out. Okay, so adding it or subtracting it doesn't really change the result finally, but we need it to be part of the general solution because it still is possible to solve the equation with that, and it basically allows us to set up the initial conditions. So yp, the particular solution, solves the non-homogeneous equation. So it solves it with the non-zero g function on the right. And so there's possibly lots of different particular solutions, but we're just looking for any particular solution. So we find a particular solution, and then we add it to the homogeneous general solution, then we get our full general solution to this equation right here. Okay, so any solution, can be, for this equation, can be written in this form. Okay, if you find, depending on what your particular solution is, that'll change the constants in the homogeneous solution potentially. Okay, so how do we solve? Basically, the goal of this section is to find y sub p. We need to find a particular solution. Okay, last section we learned how to find y sub h, the homogeneous solution. We need to figure out how to find this particular solution. And the idea behind undetermined coefficients is basically just to make a guess with coefficients that we don't know, and then plug it into the equation and solve for those coefficients. Okay, and the guess should be related to what g looks like. Okay, so basically, the idea is kind of guess and check, or guess and solve for coefficients. And so the idea, kind of the trick, is just to figure out what should our guess be depending on what g is. So for a couple examples here, say g of x is a polynomial. Say, it's something like x cubed plus 3x. Then our guess, y sub p, we're going to guess looks like another polynomial, and it has to be at least as high order as the original polynomial. So for example, we might guess something that looks like ax cubed plus bx squared plus cx plus d. Okay, and we need to make sure we include all orders lower than the highest order. Okay, and I put the constants, the coefficients, a, b, c, and d here. So that allows me to guess something like this form, plug it into the equation, and then we can try and solve for these coefficients afterward to find out what exactly is that particular solution. Okay, but this is our initial guess. if we had something that looked like, let's see here, cosine of x, our guess needs to be a cosine x plus b sine x. Okay, so whatever, when we have sines and cosines, we need to make sure we guess the opposite as well. So we have something involving cosines, we need to include both the sine and the cosine term. And whatever's coefficient is inside of here, so we have to say we have like cosine of 2x, then our particular should follow that 2x, and it should be 2x inside of the sine as well. Okay. And then the last kind of one that we typically see is something involving e to a power, say e to the 3x. In this case, our guess will look like a e to the 3x. Okay. The reason these are good guesses is because if g is like a polynomial, we're going to guess the polynomial. When we do the derivatives of something that looks like this, we're going to get other polynomials. Okay, and so that means that when we plug it into this differential equation here, do the derivatives, we're going to get a polynomials out. So plugging this into the left-hand side, we'll get a polynomial, and that should hopefully match the polynomial on the right-hand side. If you plug in a cosine or a sine, you're going to get sines and cosines out. So that hopefully that will match sines and cosines on the other side. And e to the x, if you have an exponential, if you do the derivatives of exponential, you're going to get exponentials out. And so those hopefully should be able to match up. A couple of complications. So like, for example, you might have products of these types of things. So for example, if you had something like x plus 2 times cosine of x, your guess should look like ax plus b times cosine of 4x plus cx plus d times sine of 4x. Okay, so when you can have like polynomials multiplying by cosines, sines, and exponentials, just make sure you include all the lower terms in your guess. If you have something like x squared e to the 2x, your guess should be ax squared plus bx plus c times e to the 2x. Okay, make sure we include all these lower possible terms. If you don't include those, your equations that you're going to try and solve for these coefficients aren't going to work out. Okay, so that's kind of the idea. Let's jump into an example and see how that might actually work out. Okay, so we want to solve this differential equation here. It's non-homogeneous, we have constant coefficients, and it's linear. Let's first quickly just solve the homogeneous equation. So, forming the auxiliary equation, that's going to look something like 1/4 r squared plus r plus 1 equals 0. We want to find the roots of this polynomial. Solve this equation.
Yeah. So it's -2, and this just one.
Yeah. Right? So. Yep. So let's look here. I think so. I'll multiply it by 4. R plus 4. And you can factor that as r plus 2 squared. Yeah. So our two roots are r minus 2 repeated. So the homogeneous solution is going to be some constant, let's say c1 e to the negative 2x plus c2x e to the negative 2x. So we have a repeated root, so however many times it's repeated, we multiply by x each time. Okay, so it's good, you need to do this if you want to find the general solution to this. It just says solve this equation, so generally we're trying to find the full solution. If it said just find a particular solution, you wouldn't necessarily need to do this part. But in either case, it's generally helpful to do this because, for example, if this right-hand side was e to the negative 2x, that would tell us something about our guess as well. So if our guess is already part of the homogeneous solution, that means we need to modify it in order to get a good guess. So for example, in this case, if g of x had been 3 e to the minus 2x, normally we would want to guess the particular should look like a e to the minus 2x. Okay. However, that is already in our homogeneous solution right here. So that's not a good guess, because we know if we plug this into here, we're going to get 0 out. We're not going to get something e to the 2x. Okay. And in fact, it's repeated twice. So, our next thing we maybe want to guess is like times x e to the minus 2x. But that's also here. So that's not a good guess either. These are not good guesses. So our actual guess that we would need to make in this case would be something like a times x squared e to the minus 2x. And this is one of the situations where we don't need the lower terms. Okay, and it's basically because we already know they're going to turn out to be 0. So if you had made a guess, you could make a guess something like a x squared plus bx plus c times e to the minus 2x. But we know c e to the minus 2x, we plug that in, we're going to get 0. And we know bx e to the minus 2x, we plug that in, we'll get 0. So these terms don't really matter. Only the x squared term matters in this matter. And so our guess should be something like this. And then you plug that in, you can solve for a. Okay, but however, in this case, basically we see the homogeneous solution is completely different from our non-homogeneous term. So we don't need to worry about it in this case. So what our guess should be in this case is just a polynomial, ax squared plus bx plus c. Okay. So, and the idea is to plug it in to this equation here, and we can solve for a, b, and c. All right. So that means taking some derivatives of it. So first derivative, 2a times x plus b. Second derivative, 2a. All right, so we'll plug that in. So we have 1/4 times 2a plus 2a times x plus b plus ax squared plus bx plus c equals x squared minus 2x. All right, when we do this, we want to combine all of the powers of x. So we want to make the left side, we want it to be something times x squared. So in this case, it's like ax squared is our only x squared term, plus something times x. So we look at all of our x terms. We have 2a plus b, so 2a plus b times x, plus all of our constant terms. So we've got 2 times a quarter is 1/2. So we have 1/2 a plus b here plus c is our constant term. And that should equal x squared minus 2x. So we want these two sides to be equal everywhere, which means we can match up the coefficients. So whatever the coefficient in front of x squared, that should equal the coefficient in front of x squared here. Whatever the coefficient in front of x should equal the coefficient in front of x. And whatever the constant, that should equal the constant. So we get our equations. So it tells us that a has to be 1, 2a plus b should equal -2, and then lastly 1/2 a plus b plus c should equal 0. So now we can kind of just go through and solve. We know a is 1, so you plug in 1 here, subtract that across, that means b equals -4. All right, we plug that in here, we have a is 1, so that's 1/2 minus 4 plus c, 0. Add that across, so we have plus 4 minus 1/2, it'll be 3.5. So c should be 3.5. So what does that mean? That means our particular solution is x squared, 1x squared, minus 4x plus 3.5. Right? And then the general solution then is just our homogeneous plus our particular. Just these two parts added together. Okay. You have any questions on how that worked?
No.
Okay. So that's the main idea here is always we make a guess, try and make a good guess based on what the right-hand side is. We'll plug it into the equation, combine all the terms, and match up coefficients. Okay, and the reason we can match up the coefficients is because we're not just trying to find like a point where these two things are equal. We're trying to find what are the coefficients where these two sides are exactly the same. Okay. All right. So that's kind of the general example. All right, let's try another one. Okay, so again, a good idea is to find the homogeneous solution first. So if I do that, we have r squared plus 1 equals 0. Let me just check that I wrote this down right. Yeah. Okay, so the roots of this are, we spread that across, square it. So we basically get r is plus or minus square root of negative 1 or I. Okay, so this is a complex root case, and those always come in pairs, which means that our solution, our homogeneous solution, y sub h, is when you have like a plus or minus b times I, so it's e to the ax times cosine bx plus sine bx. So it's going to be c1 cosine of 1x, so cosine of x, plus c2 sine of x. Okay, I think that's right. All right. So that's our homogeneous solution. That tells us something about our particular solution. Okay. Just looking at this particular solution, what we would want to guess is something like this. We'd want to guess ax plus b times sine of x plus cx plus d cosine of x. Because we have an x in front of the sign, so we need to include the lower terms in general. However, we know these lower terms here are actually represented in the homogeneous case. So I think we can kind of just ignore these two constants right here, b and d, because b times sine and d times cosine is just going to be 0. It becomes 0 on the left-hand side, so we don't need to worry about those. So we really just need to worry about these two coefficients here, a and c. So let's find the derivatives. It's gonna be hard enough. So ax times sine, it's gonna be a product rule. So we have a times sine x plus ax cosine of x plus c cosine of x plus c or minus cx sine of x. And that's the first derivative, and then we need to do the second derivative. I get some same things. We have a times sine is going to be a times cosine ax cosine will be a cosine of x plus ax or minus ax sine of x plus c cosine, so that'll be plus c or minus c sine of x, and minus cx, we have minus c sine of x minus cx cosine of x. All right, so that's quite a bit. Let's combine all the sines and cosines together. So cosine, we have a plus a, so 2a minus cx. We have 2a minus cx times cosine of x. And then we have the plus the sines. We have plus we have minus 2c minus ax times sine of x. All right, and then now we actually plug it into the equation. So that was just finding the second derivative. So we have this, so y d double prime plus y p is this plus our original guess. So we add these two things together. And I'm seeing that I might have made a mistake here. So we add this plus the cosine here, we have 2a minus c times x plus c times x cosine of x. And then we have plus minus 2c minus ax plus ax sine of x. All right, so that is not too good. So we see that these cx's cancel. Right, so we have the left-hand side becomes 2a cosine minus 2c sine equals the right-hand side up here, 2x sine of x. All right, so why is that not good? So we match up the coefficients here. So this, we should really think about this as, on the right-hand side, as like 2x plus 0 sine of x. So the constant in front of the sign, so this is saying 0 should equal minus 2c. And then we have plus 0 times cosine of x. That was also saying 2a should be 0. So both those go to 0, and that's not good. That means that our guess didn't work out. So what really probably I should have done is up here in our guess, we should have gone all the way up to x squared, I think. Unless you see a mistake somewhere else. So let's try that out.
I don't think I see.
So, right, and so we end up with the thing where we don't have any x terms left on the left-hand side here, which is not good. We need to have some x times sine terms. So let's maybe try again with a new guess. Yeah, this happens sometimes, and that's okay. we have to make a different guess. So let's try and guess ax squared plus bx times sine of x. So again, I don't need the constant because I know that'll go to 0. Plus cx squared plus dx cosine of x. All right, and we have to do 2 derivatives of that. So that's going to be quite an ordeal. So let's just kind of, let me check through it here a little bit. So first derivative, we have 2a times x plus b sine of x plus ax squared plus bx times cosine of x plus 2cx plus d cosine of x plus cx squared plus dx sine of x, and then there's a minus sign. Okay, let me just rearrange that to a little bit nicer. So add the signs together. So we have minus cx squared plus 2a minus d times x plus b times sine of x plus cosine terms. We have ax squared plus bx plus 2c, b plus 2c x plus d times cosine of x. All right. Now the second derivative, again, we're going to have minus 2cx plus 2a minus d, all that times sine, plus minus cx squared plus 2a minus d x plus b times cosine plus 2ax plus b plus 2c times cosine minus ax squared plus b plus 2c x plus d sine x. All right, and again, let's kind of combine those sines and cosines. So we have minus a x squared. The x terms, we have minus b. We have minus 2c, another minus 2c. So that'll be minus 4c times x. And then we have 2a minus d, and then we have another minus d, so plus 2a minus 2d, all that times sine of x, plus the cosine terms. Cosine, we have minus cx squared plus 2a minus d, so plus the x terms, so we have 2a minus d, and then we have plus another 2a, so we have 4a minus d times x plus the constant terms b plus 2c plus another b, so we have 2b plus 2c cosine of x. Okay, so that's y double prime. So if we add then plus yp, what are we going to get here? So we're going to add x squared plus bx to the sine terms. So we have all right, that's good. So we have an ax squared here minus an ax squared. So those cancel out. And so we have, and then we have a plus bx minus a b. So we have minus 4c times x plus 2a minus 2d sine plus, see the cosine terms, we have a minus cx plus cx squared, those will cancel. The plus dx and the minus dx are going to cancel. We just have 4a times x plus 2b plus 2c times cosine of x. All right, and we compare that to our right-hand side, which was 2x times sine of x. So it tells us that whatever's in front of the x sine x needs to be 2. So that means minus 4c equals 2. And all the other coefficients are 0. So 2a minus 2d here, that has to be 0. 4a needs to be 0 in front of the x. And then the 2b plus 2c has to be 0. 2b plus 2c should be 0. All right, so we need to solve these equations. So that tells us that c is negative a half. This tells us that a needs to be a 0. If a is 0, that means this one, d, is going to be 0. And if c is negative a half, plug that into here. That'll get turned that to negative 1, added across. We have 2b equals 1. And then that means that b has to be positive a half. All right, so we plug all those back into our particular solution back up here. So that means that our particular solution is, so b is a half. It's going to be 1/2 x sine x plus c is negative a half, so minus 1/2 x squared cosine of x. All right, so that's our particular solution. If we add it to our homogeneous solution from before, that'll be our full general solution. So that's quite, that was a long process, but it really is just calculus and algebra. And it's okay, in these situations to make a guess and then try again. And really, I guess maybe the key thing that we should kind of pick up from this example that I didn't quite get right away is that we had our homogeneous solution overlapped with our original guess, okay? And so not only does it just get rid of these lower terms, really we still need to scale up one order before in our guess. Okay, so because we had sines and cosines in our homogeneous solution, our particular solution, we start with our original guess, and then we really still need to scale it up one version. But it also allows us to drop the lower constant term. Okay. So in order to get a solvable system of equations, we need the x squared terms. That we saw that in that we still had an x squared term here in our particular solution. Okay, so that was necessary. And so when you have a situation where your initial guess overlaps with your homogeneous, we need to scale it up by 1 in this case. If we had like a repeated root, if this was repeated twice, we'd need to scale it up twice. Okay, 2 orders. All right, but it really just comes down to working through the calculus. Then you're going to set up equations, and then it's just kind of algebra from there. And so it can get It can get a little long. I mean, like solving 4 equations for 4 unknowns. If these hadn't been zeros, that could have been quite a long ordeal. And again, this doing all this calculus was quite long. But so in practice, you could use some sort of calculator. If you wanted to use your computer to do some of this calculus and solving the equations for you, that would be fine to try out on your own. Okay, but you should also be at least pretty comfortable doing these computations as well. All right. Let's look at this last example here. So, again, a good first step is to set up solve the homogeneous equation. So our auxiliary equation in this case is going to be r cubed minus 6r squared equals 0. So factoring out r squared, we get r minus 6 equals 0. So we have 0 repeated twice, and then we also have 6. And so our homogeneous solution, 0 is a constant, so it would be like a constant C1. When we repeat it, we got to multiply by x, so it would be C2x. And then 6, we have plus C3e to the 6x. So that's our general homogeneous solution. Okay, that's pretty easy. I mean, that's pretty nice. Pretty easy to do. So you should be comfortable with that. So that's our homogeneous solution. So now we want to find a particular solution. And we're going to make a guess based on this right-hand side here. The right-hand side is a constant plus a cosine minus a cosine. So for the constant, normally what we guess is our initial guess should be something like a constant, and then we'd have plus cosine of x plus c sine of x. Okay. However, this constant here is already represented in our homogeneous solution. So that doesn't, we know that we plug that in, we're going to get 0 out. It doesn't do anything. Okay. So we want to scale it up. So normally you try an x term, but that's also an homogeneous. Okay. So we need to go twice. So really what we should guess is a x squared plus b cosine of x plus c sine of x. Okay, so in this case, again, you normally, if you had an x squared term on the right-hand side here, your guess would need to include the linear and constant terms as well. Okay, but the linear and constant terms aren't needed in this case because they're already part of the homogeneous solution. Okay. If, let's just kind of do another kind of hypothetical. If, for example, instead of 3, I had something like 4x squared minus 2, and I had this repeated twice, I needed to scale up. So my guess in that case would be, scale it up twice, would be like a x to the 4th plus b x cubed plus c x squared. And again, I can take a polynomial. So an original guess would be a quadratic. You need to increase it by 2 orders because it's repeated twice to one with the 4th power, but then I can leave out the linear and the constant terms because we know they'll go to 0. Okay, so same here. I started with a constant, I increased it by 2 orders, but I can leave out the bottom 2 orders, the linear and constant terms. All right, so that's our guess. Let's plug it in and see what we get here. So got to do the first derivative, 2ax plus or minus b sine x plus c cosine x. The second derivative will be 2a and then minus b cosine x minus c sine x. And we need to get a third derivative here because our equation involves a third derivative. So you do that, the constant goes away. We're going to get plus b sine of x minus c cosine of x. So we plug that into our equation. So we have third derivative, so b sine of x minus c cosine of x minus 6 times the second derivative, which is this term right here. So minus 6 times 2ax, or 2a, no x, minus b cosine minus c sine, and that should equal 3 minus cosine of x. All right, so we want to combine all the like terms together. So first let's get a constant term. So we have minus 6 2a, so that's minus 12a. Now let's get our cosines together. We have minus c, plus minus c, and then we have plus 6b, minus 6 times minus b, cosine. And then our sines we have plus b, and then we have minus 6c times minus 6 times minus c is going to be plus 6c times sine. And so that equals 3 minus cosine. All right, and the last step is to match up our terms. So we have constant term, should match our constant term. We have minus 12a is equal 3. Our cosine needs to equal our cosine term, so we have minus c plus 6b should equal minus 1. And then we have no sine term, so the b plus 6c should equal 0. All right, so our a, divide that through, minus a quarter. And then we've got these two equations here. So let's see here. B equals minus 6c. So if that's the case, we have minus c plus 6b times negative 6c. So that would be minus 36c equals negative 1. So solving that around here, that means that c equals minus 37, so 1 over 37. And b equals minus 6 times that, so it's going to be minus 6 37ths. All right, so the particular solution then, minus a quarter plus, c was 1, plus, so negative 6 37ths cosine plus 1 37th sine. Okay, be the particular solution. And the full solution then would be the homogeneous. So c1 plus c2x plus c3e to the 6x plus this particular solution here. So plus, sorry, I forgot. So it's actually, the a is from the x squared here. So b minus a quarter x squared. So plus negative a fourth x squared minus 6 37ths cosine of x plus 1 37th sine. So that would be the full solution of that differential equation right there. And so that's the idea. It's always making a guess. You need to do a little bit of practicing about how you form your guess, and it's going to depend sometimes on the homogeneous solution. Make sure you include all lower order terms, plug it in, you'll get a set of equations, and try and solve those. If you can't seem to solve those equations, you need to go back and rechange your guess, increase the order of the polynomials perhaps, try again, and see if you can solve those equations. So it's really just kind of, again, just guessing and checking. And if you make smart guesses, then things work out and you're able to find these particular solutions, which allows you to solve the non-homogeneous equation. Okay, so on Thursday, Jasmine will talk about a slightly different way to find those particular solutions called variation of parameters. Okay, so you can also find this as variation. Okay, so I mean, kind of one of the key drawbacks of this approach is that really it only works with like polynomials, sines and cosines, and exponentials. You know, if you had something else, if g of x, even if you started doing like sine of x squared, things don't really work out because once you do things like this, if you make a guess like this, the derivatives don't necessarily match up. Or if you had g of x is like the natural log of x, it doesn't make sense to guess natural logs because the derivative of natural logs is not natural logs. And so things are more tricky when functions don't turn into derivatives of themselves, kind of. So like these are nice because when you do the derivative of a polynomial, you get another polynomial. When you do a derivative of sine and cosine, you get sines and cosines. When you do derivatives of exponentials, you get exponentials. And so this approach works. But if you do anything else, when you do the derivatives, your particular solution is not going to look nice and it's not going to be able to match up terms like we're doing right here. Okay, but there are other things you can do, and that'll be talked about on Thursday in the next section.